So, magnetic field you would find around a bar magnet, for example. Your bar magnet would be typically labelled north and south. What do we mean by north and south? Well, what we actually mean is north-seeking and south-seeking pole. How do we come up with that? If we were to take our magnet and we were to suspend it freely so that it is free to rotate, then this end would point towards the North Pole of the Earth and this end would point towards the South Pole of the Earth, naturally enough. Not absolutely exactly geographically north-south. The magnetic poles are slightly offset from the geographic poles, but basically near as makes no difference from an observational point of view. It points north-south. Now, we know we have a law of poles that north and north or south and south, if we brought two magnets together, two norths or two souths would repel. But if we have a north and a south, they would attract. So our law of poles, like poles repel, and like poles attract. That's pretty much what we have done at GCSE with magnets. We talked about electromagnets, of course, and we will look a little bit more at that in this section at A level, but basically that's what we said about magnetism. So let's then look at the field around a bar magnet. The field around a bar magnet would look very much like this. And you can see the field lines are closer together at the poles and further apart, further away. And this indicates the strength of the magnetic field. Notice that the field lines never touch, they never cross. So if you're drawing a magnetic field or a gravitational field or an electric field, the field lines don't touch, they don't cross. So, if we were to bring two north poles together or two south poles, which would look just like this, except the field lines would be going the other way, towards the south poles, then you have a point between the two where there is no net field. Again, we'll come across this with our gravitational and our electric fields. You can have a neutral point where there is no net field. So you've got why we call them north and south. You've got the pattern around a bar magnet. You've got the neutral point. You've got the idea that how tightly packed the field lines are is an indication of the strength of the field. So let's get a few definitions in place then. What is a magnetic field? I'll move this out of the way so you can see. Well, magnetic field is a region where, if you compare your electric field or your gravitational field definition, you had unit charge, unit positive charge for an electric field, unit mass for a gravitational field. Here we have moving charge. The magnetic field is a region where moving charge experiences a force. So we had mass for gravitational fields, we had charge for electric fields. Magnetic fields are a region where moving charge experiences of force. Magnetic field line, well, this was the path taken by mass placed in a gravitational field, the path taken by positive charge placed in an electric field, and this would be the path taken by a free north pole placed in the field. Now, there's no such thing as a free north pole, so we are imagining this is a thought exercise. Flux, well, lines of flux are field lines. Another way of expressing it. But we talk about flux because we talk about flux density, and this is the number of field lines acting at 90 degrees to unit area. Units of flux, we should add that in there while we're at it. Units, Webers, capital W, small b. And the units of flux density, well, you should know that from GCSE, Tesla, capital T, and that is Webers per meter squared, fairly obviously. The symbol for flux is phi. The symbol for flux density is B. So, a little recap of GCSE. So let's consider a conductor, straight conductor of length L meters, carrying a steady current of I amps at 90 degrees to a magnetic field flux density B Tesla. It will experience a force F in newtons where F equals B I L. Now, that is not news to you. You've seen that before at GCSE. So, we have the flux density B is the force per unit current length. If I rearrange this, B is F over IL. It is the force per unit current length. Okay? So, we have then, if we were to put that in terms of units, we know that the units are Tesla, but 1 Tesla is a Newton per amp per meter. So let's define for ourselves the Tesla. So a magnetic field has a flux density of 1 Tesla if a conductor of length 1 meter carrying a current of 1 amp at right angles to the field experiences a force of 1 Newton. Now, that's our definition of the Tesla. We also earlier talked about flux. We said B is flux density. We said that phi is the number of field lines per meter squared, and phi then is B times A. And this is Webers per meter squared. So B would be Webers per meter squared. So we've got Webers per meter squared, we've got Newtons per amp per meter, we've got Tesla. Okay. Now, along with this, of course, you've got Fleming's left-hand rule. I'm not going to write that out, but Fleming's left-hand rule allows you to predict the direction of this force that we've been talking about in F BIl. And what Fleming said was you place the first finger, second finger and thumb of the left hand mutually at right angles. The first finger is the direction of the field, second finger is the direction of the current, and the thumb is the direction of the thrust or the motion, the force. And this is conventional current. So this is a flow of positive charge. So if your electrons are flowing from right to left, the current is flowing from left to right. Okay? Flow of electrons that way is a conventional current that way, and vice versa. So there you have a recap of F BIl from GCSE. You've got the definition of the Tesla, which we didn't do at GCSE. You've got the connection between the flux density and the flux. And you've got 3 different ways of expressing the units of flux density: Newtons per amp per meter, Tesla, and Webers per meter squared. Let's now connect this macroscopic big picture F BIl force on a conductor of length L carrying a current I at right angles to a field flux density B Tesla let's bring that down to a microscopic level. Let's look at what's happening inside your conductor. So let's consider a conductor. Oops. And let's say we have a cross-sectional area A, and we'll take a section of this conductor between X and Y. Now, let's say that the electrons are moving with a speed v meters per second. Now, although we don't need to know this, in order to derive this expression, we need to know that the current in a conductor is the number of electrons per unit volume times the cross-sectional area of the conductor times the drift velocity of those electrons times the electronic charge. This is not an expression which is currently on the AQA syllabus, but it's important for this derivation. So, if we make our length xy v meters, then in 1 second, every electron between X and Y will pass Y. The electrons are flowing that way, right? So the number of electrons we're talking about here and therefore the number of electrons per second passing Y, well, that would be the number of electrons per unit volume which is n times the volume, which of course is cross-section area times length, NAV. So the force on the conductor equals BIl, and this is the force on all the electrons combined. This is the free electrons. And this, of course, is number of free electrons. So that is the force on NAV electrons. Since L is V, I should probably have written that in as V, because that's the number of electrons in that volume. So we have B times NAVE times V again, so B times NAV squared times E is the force on NAV electrons. So if we divide by NAV, that's the force on one electron, free electron. So if we were to term this small f just to distinguish it from the other one, that would be B. V squared divided by V would be V. N, A, leaves us with an E. BVE. So that's the force on a single electron travelling at velocity v meters per second at right angles to a field flux density b Tesla. If this was some other charged particle, then it would be b v q, where q is the charge on that particle. Now let's look at how those electrons behave, or those charged particles behave, when they enter this magnetic field. So here we have our beam of electrons, charge E of course, speed v meters per second, and we have a force equal to b v e on those electrons. Now if we apply our Fleming's left-hand rule here, our first finger would be pointing into the page, our second finger would be pointing to the left because this is a beam of electrons. So the conventional current is flowing to the left if the electrons are flowing to the right. So we have field into the page, we have current back to the left, which means of course that at this point the force is that way. Now if we were to follow on round to here, so if we have an electron at this point, then again we have the field into the page, we have the current going up the page at this point, tangentially to this circle, which again means the force is towards the centre of this circle. And what you find is that this is a centripetal force. Now we've come across this before in our work with electric fields and gravitational fields. So here we have a centripetal force in a magnetic field, and that means that your force, which equals BVE or BVQ generally, equals mv squared over r, or mr omega squared, where omega of course is the angular speed. So we have circular motion. Let's have a look at some questions to practice our knowledge and understanding here. So these are on Isaac physics. Which of the diagrams below shows the correct magnetic field around the bar magnets? If we take them one at a time, A shows north and south facing. We'd expect the field lines to run from north to south, so that's not right. Here we have north and north facing, and again we'd expect the field lines to repel there, and they don't. So that's wrong. In C we have field lines running from south to north, and that's wrong. In D we have two souths, field lines running into the south, which is what we'd expect, neutral point in the middle. So the answer must be D. And of course it is. If we then go on a little bit more quantitative, we have magnetic flux density between two permanent magnets is 6 times 10 to the minus 3 Tesla. A wire is placed at right angles to their magnetic field. And carries a current of 4.5 amps. And the length of the wire within the field, 0.13 meters. We want to know the force. F, of course, equals BIL from GCSE. We have 6 times 10 to the minus 3 times 4.5 times 0.13. And if we do that, we have 6 times 4.5 times 0.13, 3.51 times 10 to the minus 3, well that's 3.5. Newtons. And there we go. Then we have deflecting ions. So here we're looking at not F equals BIL, but BVQ. So we have a region containing a uniform magnetic field, flux density B, particle of charge Q, traveling at right angles to the field, deflected as shown. So we have the field going into the page. Find the expression for S, the length of the particle's path in the field, in terms of B, P, and Q. We have a momentum P. I missed that, which of course is MV. So you would say the force on it is BVQ. Sorry, let's make that the right kind of Q. And we know this is a centripetal force. It is at right angles to the motion, which equals mv squared over r. And S, the arc length, is r theta, where theta is the angle moved through. So we've got BVQ equals mv squared over r. So we've got BQ equals mv over r. So r then is S over theta, but if we look at our diagram, theta is pi by 2. So r is S over pi by 2, which is 2s over pi. So let's put that in there then. P is BQ times 2s over pi. If we then make S the subject, because we're asked for an expression for S, S then is pi times P over 2 BQ. And if we put that in here, we'd have S equals P times pi divided by 2 times B times Q. It is correct. What I've forgotten are the brackets around that. So, we have the wire between the magnets, We have the fields around the magnets. We have the deflecting ions. Finally then, an electron in a magnetic field. So, let's get rid of all of this then, and start again. So we have an electron with a charge of minus 1.6 times 10 to the minus 19 coulombs, of course. Velocity of 2.35 times 10 to the 7 meters per second. So I'm noticing 2 and 3 sig figs here. And I've got a flux density of 3.4 times 10 to the minus 2 Tesla. And I'm asked for the force. Well, that's BVQ, of course. And we've got 3.4 times 10 to the minus 2 times V, which is 2.35 times 10 to the 7 times Q, 1.6 times 10 to the minus 19. And if we do all that, we'll get 1.3 times 10 to the minus 13 newtons. And we have a minus here, but we're asked for the size of the force, not the full vector value. 1.3 times 10 to the power of minus 13, and newtons.